Okay, in this section we're going to look at linear approximations and then something called differentials. So remember, we can use a linear approximation to estimate a value on a curve by using a y value from a tangent line. So do you remember where else we did this? This says from chapter 2. What section was this problem in? Now what you can do differently is use shortcuts for derivatives, because in the section in chapter 2 when we did this, we had to use the limit definition of a derivative to find the derivative of the square root of x. But not now. Now we can say, okay, we know that f prime of x is 1/2 x to the negative 1/2, or rewritten simplified, this, right? So now if we want to approximate the square root of 0.99, then if a is 1, remember that the point slope form really just comes from your approximation, that's a y value, minus a y value equals your slope times x minus x. Now, I repeated the same letter a lot of times, which is not good. So what do I want to do? I want to say, okay, if I want to approximate a value that's near something else, then we're going to use this a value that everything is close to in those three places. Okay, so that this y matches this x, and then we're using the slope of the tangent line. And then, so for instance, in this particular problem, I can say that the square root of 9.99, approximately equals, and so that's this thing right here, is approximately equal to f of 1 plus f prime of 1 times 0.99 minus 1. So you figure that out on the calculator, realizing that, this is your function and this is your derivative. So go ahead and actually evaluate this and see what you get. Hopefully you got the right answer, and compare this to the actual square root of 0.99. If you want, you can also now, as a reminder, work on these or try these next two problems. Now the next question is, are these approximations overestimates or underestimates? And you need to remember how we know if a tangent line approximation is going to be too high or too low. Okay, I'm not going to tell you again because I've told you before, so look it up and you're going to have a question on that. If you're watching this video and you're not in my AP Calculus class, then you're not seeing that, there are some interactive questions on Edpuzzle that go with this. Okay, now the best way to understand differentials, the notation for differentials, and how dy and dx compare to the change in y and the change in x, and remember this represents the change in y and this represents the change in x, is to look at two things in particular, the slope of a secant line and the slope of a tangent line on a curve where we have the tangent line drawn. Okay, the secant line would join this point to this point. Now I tried to make this x value right above it, and the tangent line obviously is drawn right here. So what we have is a change in x. We're going from -2 to some other value, maybe -1.5, -1.4, something like that. And the change in x on the secant line and the change in x on the tangent line, those are both represented by this little curvy bracket down here. And both of those, whether we're talking about the change in x on the secant line or the change in x on the tangent line, they're the same thing. So delta x and dx are the same things. Now, how did I just make dx mean something? Well, if the slope of the tangent line is dy over dx, and that's our Leibniz notation, dy over dx, and we also know that the slope of the tangent line is the rise over the run, then that must mean that dy is representing that rise and dx is representing that run. So dx is the change in x on the tangent line, and delta x is the change in x on the secant line. So those are the same. Now, if we look at the change in y values, we can see, now I've drawn two little brackets out here, this one and this one. This one represents the change in y on the tangent line. In other words, this red dot to this maroon dot, okay? So we're going to call that dy, where the change in the y values on the secant line goes from the blue dot down to the red dot, and that is going to be our delta y. So you see in this case, in all cases actually, dx and delta x are the same. But unless this curve is actually a line, dy and delta y are going to be different. And dy is very easy to find, which you'll see in the next few slides. And it's a very good approximation for delta y, and that's why we're using these things called differentials. Okay, so now let's just look at notation. In derivative notation, or you know, when we found the derivative of y equals 3x to the fifth, we could write dy dx equals 15x to the fourth. In differential notation, since dy means something and dx means something, they are changes in, you know, x and y, then we're going to have them separate, or separated, I guess. So dy equals 15x to the fourth dx. It's basically like you took both sides of this derivative and multiplied them by dx. And that's differential notation. So in general, you want to know that given y equals f of x, dy is going to equal the derivative of your function dx. And that is all you need to know, which really means you're not learning anything new, just a different way of interpreting something that you already know. Okay, here's a problem that I want to make slightly interactive. This is number 18 from your book, from your Stewart book. And the function given is y equals the square root of x. We started looking at that at the beginning. Find the differential dy. Okay, so what's the differential going to be? Dy equals the derivative of that function dx. That's it. That's all you need to do. Okay, so nothing new. Now evaluate dy and evaluate delta y. If x equals 1 and dx and delta x, which are the same, both equal 1. So that's where I'm going to let this be a little bit interactive. What you need to do in part B is figure out what dy is by plugging in the values that they give you into this equation. So you come up with your answer for dy, and then you also come up with your answer for delta y. That's the change in y on the actual curve, correct? Okay, so what does this mean, and do you really, realize what you're doing here? Let's skip to C, where we're sketching a diagram, and then that might help you with the second part of B and what we're actually doing. So let me pick a different color, and let me sketch the square root of x, Let me make sure that I am including x equals 1 on my graph, and if my change in x is going to be 1, then how far do I have to go on my graph? Or the other x value that I'm looking at is going to be where? Okay, hopefully I have paused long enough to give you time to answer the question. So here is my square root of x graph, and I'm going to, I don't know, pick a couple of places here that hopefully I can illustrate what I want to do on my picture. So here's my 1, and here's my 2. And I hope you got that answer, because that's how your change in x, or your delta x, is going to be 1, right? Is if you move from 1 to 2. So let me pick 3 different colors for my points. We'll pick orange for the point where we make our tangent line, because we have to use a tangent line, right? This is all about linear approximations. Let me use blue for the other point on the curve, where in this case delta x is 1. And let me use maroon, because this is how, I know I didn't use orange on the first one, but for this corresponding x value, but the y value on the tangent line. So I want to show the line segments with lengths dx. So here's the line segment with dx. Is that the color I want to use? Sure. No. Let me make dx that color. So dx is this length right in here. Maybe I want to draw it down here, right? Now I also want to draw dy and delta y. So dy, I'm pausing when I talk so you can try to get this yourself first. Do you know what dy is going to be? Okay. Hopefully you knew it was that, right? It is from here to here, as far as your y values go. And then lastly, let's pick one more color for delta y. Delta y is the difference in y's on the curve. So if I go from here to here, of course I'm going to have the same bottom, right, as the green one. That's the length of my delta y. So you still can go back now for part B. If you didn't get the answer to the question the first time in Edpuzzle, I will give you another shot, because you saw one of your answer choices was I don't know yet. So you either gave the answer already or you said you didn't know yet. Now I'm giving you one more chance. Can you figure out the difference in y's from that point to that point? Can you figure out this length? That's your last question. And here's your homework. Now 16 through 20 you would want to wait and do after you watch the next video.